Okay, so this is not always true. Here's an example. I cross J. What is that? Well, let's do I cross I. I cross I is equal to 0. Okay, we saw that already. 0 vector. So this is equal to 0 vector cross J, which will be 0 vector. But if I change my bracketing, I get what? Well, in fact, I'm going to get I cross, this will be K, which I'll show you in a second why. Then IK is going to be negative J. Let me do these calculations below. I cross J is determinant I, J, K, 1, 0, 0, 0, 1, 0, which is this determinant is 0. The determinant for J is 0 as well. So the only thing surviving, actually, you know what's smarter here? You know what would be smart here? What would be smart here? Do a determinant down the third column. So all I get is K times this determinant, so I just get K. And then I want to do I cross K. Boop, bop, beetle. Dun, dun, dun. And then I'll do a determinant down the second column, giving me negative J times 1, 0, 0, 1, which is negative J. Here I did the third column. Okay. All right, so my answer to this question is nope. Okay, so in one version of bracketing, I get the 0 vector, but in another version of bracketing, I get minus J. So very different. Okay, exercise for you. Work out all products of the form, I cross J, I cross K, J cross I, J cross K. Okay, all possible combinations. Okay, some of them are 0, and this one is just the negative of this one, so you can save yourself some time. So pause and copy and try that. And what you should arrive at, what you can summarize your answer as, is a diagram that goes like this. Okay, so it's a circle with arrows. What I'm saying here is that if I go I cross J, I get K. And if I go K cross I, I'm going to get J. But if I go backwards, so against the arrows, you can see here, I cross K is actually going to give me negative J. So if you go backwards, you get negative. And what else? I cross I is 0, j cross j is 0, k cross k is 0. Okay, pause and copy all this. So I think maybe you've seen this before in some form or another. The proof is our labor. Lots of labor for part 1 here. You can try it if you want. So prove Lagrange's identity via labor. Okay, so lots of work. Okay, so what you'll have to do is you'll have to say, okay, U is equal to U1, U2, U3. V is equal to V1, V2, V3. And you have to work out the left-hand side and work out the right-hand side, which I think I screwed up. Yep, I forgot a squared. I'm missing a squared here. Should be power of 2. Right there. So what was I saying? Yeah, work out both sides, long calculation. And then part 2 is easier. You'll need sine squared theta plus cos squared theta is equal to 1. Okay, totally optional. You can, if you're bored on a Sunday afternoon and you want to spend half an hour calculating, then try this. Okay, more interesting perhaps is the geometry of the situation. We're going to see that this is the area of this parallelogram here. Let me convince you of that. Area is equal to base times height, length of U times L. Or these are both real numbers. Sorry, I use this dot for my multiplication in the reals as well. I hope it doesn't offend anyone. Now, what's L? I'm going to use some trig here. L is sine theta. Sine theta is SOHCAHTOA opposite L over hypotenuse. So L is equal to V sine theta. Put this in a thinking bubble, thought cloud rather. So my area is U V sine theta, which by the property is the length of U cross V.